Hello, and thank you very much for having me. I feel truly humbled to be speaking after such a specialist on masonry construction, but hopefully I'll be able to share with you what we do in our practice. I would like to tell you a story of a building, and for once I don't want to concentrate on the aesthetic judgments we made or its urban setting, contextual design. What I want to talk about is really look under the skin and see how the way we build our buildings is intrinsically linked to the quality of the environment we create, to its success, to the success or failure of this environment. The building I'll be talking about is a new brownstone built in New York on Upper East Side. It's been designed as a replacement for the 1960s school building and a companion piece to an older house which was built in 1918. It was made of stone, and one of the main questions we had to face was how do we build our facade and building so that it can actually stand side by side and hold its own. And clearly what we wanted to do is think about what has been considered a standard way of construction nowadays. So cavity wall, you will recognize it really easily. There are expansion joints, whip holes, and if it's a brick building, it will have a stretcher bond. They all come from the fact that for dry environment, it relies on the provision of the cavity, which is concealed behind a thin layer of brick or stone, which needs supported on steel angles at every level and tied back with the ties. Every level moves separately from one another, which means that movement joints are needed horizontally. Furthermore, the thin brickwork or block or stonework expands a lot, meaning that you need vertical joints as well. So let us imagine what would happen if this was the way we built our building. And yes, you would have at least 2 horizontal joints and 1 vertical one. What's more, we need to turn a corner, and yes, another vertical joint is coming. Inevitably, just a few years later, it will look like that. And then the decision, do we put it on the face with a pediment, or should it face the street? This is really not a question we wanted to answer. Now, that's not enough. The thin layer of external brick is not capable of supporting any stone detailing. What you need to do is you have to fix it mechanically, and clearly mechanical fixings are prone to failure. What's more, every time the cavity is breached, either to support the brickwork or to introduce the openings, you have to introduce cavity trays and whip holes. So the rain comes, it gets into the cavity, and then dirty water is expelled through the cavity. What you end up with is staining in random locations. You can see it here in the Muse House, humble Muse House somewhere in London, or in this much more iconic building, which actually formed part of the redevelopment of Paternoster Square around St. Paul's Cathedral in London. And really, after 30 years, it looked like this. Now, believe it or not, this is a stone building. And then, once again, we've got movement joints, now we need whip holes. So, let us contrast it with a building which is also made of stone, also built in London, but it's been built almost 300 years ago, and it still looks really respectable and attractive. So, how is it different? The way it's been constructed is very different. It used solid masonry load-bearing construction, which means that all the floors and the roof, as well as architectural detailing, were built into the wall, which carried the weight all the way down to the ground. For dry environment internally, it relied on the mechanism known as an overcoat effect. The rain would come, it would be allowed to soak into the wall. The wall would be thick enough not to allow it to go all the way through. When the rain stopped, it would slowly dry out, and the wall would be dry again. And so you would say, well, the benefits of this building method are clear to see. You end up with a solid wall with all the architectural detailing and proper bonding. It all relies on gravity to stay in place. As the weights are carried all the way down to the foundations, you do not need any horizontal movement joints. And the mass of the wall means that thermal expansion is also not a problem. So no vertical joints are needed. There are no weep holes because we have no cavity. So the obvious question is, well, why don't we build like that anymore? And the answer is really quite clear. It's to do with cost, but more importantly, it's to do with time. External wall in this case is on a critical path. You basically cannot do anything with the building until every floor has been built into the wall. So is there any way we can still have the benefits of solid masonry construction while actually meeting the time requirements? And yes, there is. What can be done, you can separate the two. You can build structure and inner leaf separately, allow it to be watertight so that the inside of the building can go ahead, and then construct in front of it a solid masonry wall which is self-supporting. It carries all the weights down to the ground. It's thick enough to still perform the role of the overcoat, and only relies on the structure behind for lateral support, for keeping it vertical and not allowing it to fall away from the building. And as I said, everything, all the detailing can be built in. The water can act exactly in the same way as you've seen in the historic building. It comes in, it soaks in, it dries out. And so that's the approach we adopted in the New York building. Some of the aspects of it were very, very American. So the inner wall was built together with the structure, fully cast as reinforced concrete. We had 9-inch fully bonded brickwork behind it with a 6-inch, minimum 6-inch thick stone. Now, because of trade unions, the bricklayers and the stonemasons don't work together. So normally these two would have been built in and fully bonded. Here we needed to use stainless steel angles and mortar to get the two to work together. And you can see it here slowly rising up the corner. I'm really glad to say not a movement joint in sight. It terminates in deep cornices, pediments with acroteria, stone edicules, stone capping, and banisters, solid stone banisters, carved stone detailing to support the balconies, ending up with the solid masonry self-supporting wall, which with luck will age well and last for centuries to come. And importantly, we hope it will be a worthy companion to all the buildings standing alongside it. Now, this by no means is the largest building we built in this way. I want to show you now some buildings that we created for Lady Margaret Hall in Oxford. Everything you see highlighted in dark are new student buildings. They were built of red brick with Portland stone. They had inner leaf, which was, depending on the size of the building, either made of load-bearing reinforced concrete block and blockwork on upper levels, or concrete frame with metal stud infill, and then the external wall of 215 millimeters deep brickwork with Portland stone. And here it is, one of the buildings with student rooms on the upper levels and common rooms on the lower levels, with the stone colonnade roofed, all overlooking college gardens. You can see on the plan internal structure highlighted in green with insulation applied on top, and then externally the load-bearing wall, which is built of combination of brick and stone. And here the same elements built, shown in section. As I said, you build the structure and the frame first, and trying to make it as fast as possible. So, for example, the hollow core precast slab is used. So this part of the construction goes ahead quite quickly. You then apply insulation, and on top of it, a flexible Breve membrane, which is inserted between the inner leaf and the external wall. It performs two roles during the construction while the building is being built. Together with the windows, it throws the water off the facade and keeps the inside dry. It also, once the brickwork is actually in place, is our last line of defense. If any moisture does get through to the inner part of the brickwork, the membrane can throw it out of the inside of the wall, either over the windows or over string courses. The windows need to be fixed to the inner leaf so that they can be, the Breve membrane can be sealed against them. And here you are, the insulation is being applied, the windows are already in place. We got Tyvek, which is our Breve membrane fixed to the windows, and the fully bonded facade together with stone window surrounds goes slowly up against it. And here at the top, we've got a cornice with tiles being applied to the roof. And you can just see the remains of the temporary rainwater system which is installed to allow the brick wall to come slowly up. Now, the importance of all of it is, what it means is the brick wall is taken off the critical path. You can give it time to be built properly while the inside, the first fix and second fix take place inside the building. Sorry, it's stuck. Oh yeah, now it moved too fast. No, it's good. So here we are. In order for this 9-inch brick wall to perform the function of an overcoat, the specification of the bricks and the mortar is very important. You have to specify bricks which are strong enough to be capable of going up to 12 meters in height, but have absorbency which is high enough to allow the water to slowly soak in and then dry out. Crucially, the mortar needs to be a mix of lime and it has to include lime. If it doesn't, it would crack. Cement mortar would be totally inappropriate. It would create roots straight into the inside of the wall, and who wants to have a raincoat with holes? So, very important to get your specifications right. Another aspect, technical aspect that has to be taken into account is a differential movement between the inside and the outside layers of the wall. It will occur both vertically and horizontally, but a relatively simple fixing method has been devised. It consists of two stainless steel channels which are fixed at right angles to one another. One is fixed to the outside leaf, the other one to inside leaf, and there is a bolt which connects two of them. It allows for the wall to move in both directions while keeping it laterally supported, and this is all that this wall requires from the internal structure. Wrapped brick arches are incorporated into the design, and once again, in order to speed the process up, they are preformed and brought in to site and built in. Sometimes with the introduction of the stone keystones, which you can just about see high up, they allow us to create richly figured facades. It's for arcades as well as the timber colonnades with the structure supported of built-in corbels with timber window surrounds as well as plugs. And as you can see, none of it has any whip holes or movement joints. And this really brings me to something which I find almost miraculous about this solid self-supporting wall construction. This is an undergraduate building. The total length of external wall is approximately 150 meters, and I can't say we didn't need any movement joints, we needed one. It's in the re-entrant corner of the building, but that's all that was needed. And As the last building that I'll talk about in detail, I want to show you this residential building in south of England. It's Howell Hall. It had, like the previous examples, it has an independent frame, which here was built of green oak and timber with infill of blockwork, and the exterior leaf of self-supporting green oak frame with infill of lime render on wood wall slabs. This combination allowed us to create a building at the house which has all the mod cons you could think about. It has temperature control, it's airtight, it has underfloor heating. Importantly, it meets building regulations, so we were allowed to build it. And clearly, it created a comfortable home. The way it was done was a ground floor slab was built in the first place. It incorporated underfloor heating, which was fed by a ground source heat pump. The oak frame was built on top of it. It was then filled with blockwork, covered with insulation and membrane. The fireproof boards were put on top with buttons and with counter buttons allowing the ventilation. And then finally, all of it was covered with thatch and the external leaf consisting of self-supporting green oak frames with the wood wool infills. And here you go, everything that's highlighted in green is the green oak. Now, the important thing about the green oak is it moves. It moves a lot. So this is where really careful detailing has to be once again applied. So at the top image, you can see that blockwork, between blockwork and the timber posts, we needed to introduce compressible filler to allow for the movement. The render internally needed to be cut short so that it didn't crack when the timber moved. The posts are cut from the center of the tree, and they twist and turn around the center. The center stays stable, and this is where the fixings for the external, to connect external leaf, need to come to. You need to leave a space around them as they leave the timber, once again, so that they don't impede the movement, and the fixings themselves need to be flexible, so once again, they can move up and down and horizontally. And so here it is, the final product with its thatched roofed brick chimneys and half timber walls, in addition to characterful old village, sitting in the midst of all the greenery, really not giving many clues to all the technical knowledge and know-how that went into building it. So for the building to be modern, it does not mean that it has to look in a particular way. I think what it means is that it has to take the benefit of the knowledge, new knowledge, and where necessary, new techniques to produce something that will age well and last. And this is the approach that we took for last 30 years in building small and big, Gothic, classical, built of stone, brick, and the mixture of the two. And really, what I think is important, that we need to take the best that we can from the lessons of centuries of building in a traditional way, combine it with modern knowledge, and deliver buildings that will not look decent on the first day, but actually will age well. Like you said, proper detailing allows for the water to be thrown off, and if there is any patina, it actually comes on the details, making the architecture read better rather than working against it. So I'm hoping that we are able to create buildings that will last and be truly sustainable and adapt to the user's needs as the time comes.